There is a question that has echoed through the quiet corridors of human history, a question whispered in our oldest myths and broadcast in our most ambitious works of science fiction. It is a question so fundamental that it touches every one of us, connecting us in a shared and profound sense of wonder. The question is simple: are we alone? For all of our existence, this question has been a matter of philosophy, of faith, or of fantasy. The universe, in its immense and silent grandeur, offered no clues. We were a species on a single, lonely world, looking up at a sky of countless, distant, and unknowable stars, left with nothing but our own hopeful or fearful speculation. But in our lifetime, for the first time in the history of our species, that is beginning to change. The question is slowly but surely moving from the realm of philosophy into the realm of observable science. And in the autumn of the year 2023, humanity's most powerful and ambitious eye on the cosmos, the James Webb Space Telescope, stared for hours at a single, faint, red star, about 124 light-years away. It was not looking at the star itself, but at a planet that was passing in front of it, a world known by the humble catalog name of K2-18b. And in the faint, filtered starlight that passed through that distant world's atmosphere, the telescope detected something astonishing. It found the chemical fingerprint of a molecule that, here on Earth, is almost exclusively produced by life. A possible biosignature, a hint, a whisper. For the first time, the great cosmic silence seemed to be broken, not by a radio signal or an alien spacecraft, but by a faint and ghostly trace of chemistry in the air of a world that is 700 trillion miles away. This journey tonight is the story of that whisper. It is the story of K2-18b and the tantalizing secret that it may be holding. We will travel across the vast gulf of interstellar space to visit this strange and mysterious world, a planet unlike any in our own solar system. We will explore the revolutionary power of the James Webb Telescope and understand how it is able to read the secrets of an alien atmosphere from across an unimaginable distance. We will delve into the beautiful and exciting hypothesis that K2-18b may be a Hycean world, a vast global ocean of liquid water hidden beneath a thick hydrogen sky. And we will, with a calm and careful sense of wonder, examine the evidence for this potential sign of life, and also listen to the quiet voices of scientific skepticism that urge caution. This is not a story with a simple or a definite answer. It is a journey into the heart of a living, breathing scientific mystery as it unfolds, a meditation on the nature of life, and a quiet exploration of what it means to stand on the very brink of the greatest discovery in human history. Before we begin our long journey to this distant ocean world, I would love to know from which part of our own blue planet you are joining this exploration tonight. Please write your city or your country in the comments below. It is a beautiful reminder that as we look out into the great cosmic ocean, we are all together on this one single precious island of life. And if you enjoy these calm journeys to the frontiers of our understanding, please consider subscribing to the channel. Your support is the quiet energy that makes these voyages possible, allowing us to continue our travels together, always calmly, always at the pace of the universe. Our story begins not with a bold claim, but with a deep and abiding sense of wonder. The question of life beyond Earth is too important to be met with sensationalism. It must be approached with the patience, the care, and the rigor of science, but also with the open and curious heart of an explorer. The evidence from K2-18b is not a conclusion. It is an invitation. It is an invitation to look more closely, to ask deeper questions, and to imagine the incredible possibilities that the universe may hold. And so, let us accept that invitation. Let us quiet our minds, let go of our preconceptions, and begin our gentle 120 light-year journey to a dim red sun and the strange water-shrouded world that orbits it. To truly appreciate the message that may be hidden in the atmosphere of K2-18b, we must first undertake the immense journey to its home. Our vessel, as always, is our own imagination, a craft capable of crossing the vast, dark oceans of interstellar space in an instant. Our destination is a star system located 120 light-years away, in the direction of the constellation Leo. The distance is a number so vast that it almost loses its meaning. A light-year, the distance that light travels in a single year, is nearly 6 trillion miles, or 9.5 trillion kilometers. To say that our destination is 120 of these units away is to say that the light we see from its star tonight began its journey around the year 1900, the same year that Albert Einstein first published his theory of special relativity here on Earth. If we were to board our fastest existing spacecraft, the Parker Solar Probe, and set its course for K2-18b, the journey would take more than 2 million years. The gulf that separates our world from this one is an almost perfect and unimaginably vast emptiness. It is across this void that a faint, tantalizing whisper has traveled. And so, in our mind's eye, let us cross this distance in an instant. We arrive in the K2-18 system, and the first thing we notice is the star itself. It is profoundly different from our own sun. Our sun is a brilliant, yellow-white star, a great, roaring bonfire that bathes our world in a full and vibrant spectrum of light. The star K2-18, by contrast, is a red dwarf. It is a much smaller, much cooler, and much dimmer star. It has less than half the mass of our sun, and it shines with a light that is far less energetic, a soft crimson glow, more like a great celestial ember than a blazing fire. The light it emits is predominantly in the red and infrared parts of the spectrum. Standing on a world that orbits this star, the quality of the daylight would be a perpetual, dusky twilight, a world painted in shades of orange, salmon, and deep ruddy gold. But these small, cool stars have a secret and profound gift: time. While our own sun will live for a total of about 10 billion years, a red dwarf star like K2-18 is incredibly fuel efficient. It sips its hydrogen fuel so slowly that it can shine for trillions of years, far, far longer than the current age of the universe itself. This means that any planet orbiting in a stable position around a red dwarf has an almost unimaginably long and peaceful period in which life, if it were to begin, could evolve and flourish. These are the great quiet Methuselahs of the galaxy, the most common and longest-lived stars of all. We now turn our attention to the planet at the heart of our story, K2-18b. It orbits its dim red star well within the habitable zone. This is the so-called Goldilocks zone, the gentle band of distance from a star where the temperature is just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. Because its star is so cool, the habitable zone in the K2-18 system is much closer than it is in our own. K2-18b completes a full orbit its entire year in just 33 Earth days. This close embrace with its parent star leads to a powerful and almost certain consequence known as tidal locking. Just as our own moon is tidally locked to the Earth, always showing us the same face, it is likely that K2-18b is tidally locked or in a pseudo-synchronous state. This means that one side of the planet is locked in a state of perpetual endless day, forever facing the dim, red sun. The other side is locked in a state of perpetual, absolute night, forever facing the cold, empty darkness of deep space. The implications for its climate are extraordinary. The day side would be constantly baked by the star's radiation, while the night side would be a frozen wasteland of unimaginable cold. But between these two extremes, there would exist a fascinating and potentially life-bearing region, the Terminator Zone. This is a permanent, globe-spanning ring of twilight that separates the day side from the night side. In this endless sunset, the temperatures could be far more moderate. It would be a world of eternal dusk, a land where the red sun hangs forever on the horizon. This Terminator Zone could be a place of immense storms, as the planet's thick atmosphere would be in a constant, violent struggle to redistribute heat from the hot side to the cold side. And it is here, in this ring of eternal twilight, that the conditions for life might be most promising. And so our journey is complete. We have arrived in this strange and beautiful alien system. We are in orbit around a world larger than our own, shrouded in a thick, hazy atmosphere, and bathed in the eternal crimson light of its parent star. We have set the stage. And now, from our vantage point, 120 light-years away, we can finally deploy our own great eye on the cosmos, the James Webb Space Telescope, to peer through this atmosphere and begin the patient, careful process of reading the secrets that are written in its air. We have arrived at our destination. We are in orbit around the strange and beautiful exoplanet K2-18b, a world larger than our own, bathed in the eternal twilight of its dim, red sun. But we are here not just to imagine what this world might look like. We are here to understand how, from a distance of 700 trillion miles, we can possibly know anything about it at all. How can we read the secrets of a world that is, and will forever remain, an impossibly distant, unresolved point of light? The answer lies in one of the most elegant, powerful, and beautiful techniques in modern astronomy. It is an art form known as transmission spectroscopy. And our paintbrush for this art form is the most powerful instrument ever built by human hands, the James Webb Space Telescope. To understand this delicate art, let us first imagine the K2-18 system as it is aligned from our perspective here on Earth. By a wonderful accident of cosmic alignment, this distant solar system is oriented in such a way that from our point of view, the planet K2-18b passes directly in front of its parent star once every 33 days. This event is called a transit. When this happens, the planet blocks a tiny, almost imperceptible fraction of the star's light, causing the star to dim ever so slightly. By measuring this tiny dip in brightness, we can calculate the size of the planet with incredible precision. But the true magic happens not by looking at the planet itself, but by looking at the starlight that passes through its atmosphere, just as the transit begins and ends. Let us picture that moment. As K2-18b begins to cross the face of its star, for a brief period, the star's light is filtered through a thin, glowing ring of the planet's atmosphere. This is the moment that the James Webb Space Telescope has been waiting for. It can image, but for atmospheres, its power comes from transit spectroscopy with prisms and gratings. Its primary purpose is to gather the faint light from these distant objects and to spread that light out into its full spectrum of colors, a beautiful, rainbow-like barcode of infrared light. And hidden within this barcode of starlight is the secret message of K2-18b's atmosphere. Here is how the message is written. The light from the star, on its own, would create a smooth, continuous spectrum, a perfect and unbroken rainbow. But when that starlight passes through the planet's atmosphere, the different molecules and atoms present in that atmosphere will absorb very specific, very precise colors, or wavelengths of that light. Every type of molecule has its own unique, telltale absorption signature, a kind of chemical fingerprint. Water vapor, for example, will absorb certain specific shades of infrared light. Methane will absorb a different set. Carbon dioxide will absorb yet another. When the James Webb Telescope looks at the starlight that has been filtered through K2-18b's atmosphere, It sees a spectrum that is no longer smooth and perfect. It is a spectrum that is crossed by a series of sharp, dark lines, like a barcode. These dark lines are the chemical fingerprints of the molecules that are present in that alien sky. The work is incredibly delicate. The signal from the atmosphere is unimaginably faint, a tiny whisper hidden within the much louder shout of the star's own light. It requires a telescope of Webb's immense size and exquisite sensitivity, a telescope that must be cooled to just a few degrees above absolute zero to see these faint infrared signals. And it requires immense patience, staring at the system for hours and hours over multiple transits, to gather enough photons of light to build up a clear and readable signal. In the case of K2-18b, the James Webb Telescope has already delivered a spectacular result. By staring at the planet during its transits, it has given us one of the clearest spectra of a sub-Neptune so far. The spectrum shows a hydrogen-rich atmosphere with robust detections of methane and carbon dioxide. These are the building blocks of a complex and dynamic atmospheric chemistry. But most excitingly, the telescope's initial observations hinted at the absence of other molecules, like ammonia, and a lower-than-expected amount of water vapor. This was not a disappointment, it was a clue. The specific combination of what the telescope did see and what it did not see pointed towards a new and incredibly exciting possibility for the nature of this mysterious world. The data was a perfect match for a new and largely theoretical class of planet, a world that we have long dreamed of finding. The data was telling us that K2-18b might just be a Hycean world. We are poised, in our shared imagination, 120 light-years from home. We have journeyed to the dim, red star K2-18 and are now in orbit around its most mysterious planet, K2-18b. We have seen how, once every 33 days, this world performs a transit, a silent passage across the face of its star. And we understand now the beautiful and delicate art of transmission spectroscopy, the method by which the James Webb Space Telescope can catch the starlight that filters through the planet's atmosphere and spread it into a rainbow-like spectrum, a barcode of light that holds the chemical secrets of this alien sky. The long journey is over. The patient hours of observation are complete. And now, in a quiet data center back on Earth, the barcode is finally revealed. It is time to read the message. The first and most immediate finding from this barcode of infrared light was the confirmation of what astronomers had long suspected. K2-18b has a thick and substantial atmosphere, and it is overwhelmingly rich in hydrogen. This in itself is a fascinating detail. Unlike the inner rocky planets of our own solar system, Mercury, Venus, Earth, and Mars, which have thinner atmospheres dominated by heavier gases, K2-18b has retained a vast, primordial envelope of the lightest and most abundant elements in the universe. This tells us that the planet is a kind of hybrid, a missing link between a rocky world like our own and a true gas giant like Neptune. It is a member of a new and mysterious class of planets, the sub-Neptunes, which are the most common type of planet in our galaxy, yet are completely absent from our own solar system. But the spectrum revealed much more than just hydrogen. Within that primary signature, the telescope detected the clear and unambiguous chemical fingerprints of two other crucial molecules, methane and carbon dioxide. Finding these two carbon-based molecules together is an incredibly exciting piece of the puzzle. Methane is a simple organic molecule, the combination of one carbon atom and 4 hydrogen atoms. Its presence is not necessarily a sign of life. It is abundant in the atmospheres of the gas giants in our own solar system. But its existence on K2-18b confirms that the planet's atmosphere is a place of active and complex chemistry. Carbon dioxide, on the other hand, is a molecule that is deeply intertwined with the story of life on our own planet. It is the gas that plants use for photosynthesis, and it is a key component of the carbon cycle that regulates our long-term climate. To find both of these molecules in the atmosphere of a potentially habitable world is tantalizing. It opens the door to the possibility of a dynamic, planetary-scale system where these gases could be part of a complex cycle of geology and, perhaps, biology. However, on its own, this discovery is still ambiguous. A hot, hydrogen-rich world with no life could still have a chemistry that produces both of these gases. This initial finding, then, was not an answer, but a deeper and more interesting question. It presented two possible paths for the story of K2-18b. Was this simply the signature of a sterile, lifeless mini-Neptune? Or were we seeing the first hints of a much more complex and potentially living world? To find the answer, astronomers had to look not just at what was there, but at what was missing. And this is where the story takes its most exciting turn. Based on all of our standard chemical models of a hot, hydrogen-rich atmosphere, scientists fully expected to find one other molecule in great abundance: ammonia. The combination of nitrogen and hydrogen in such an environment should, by all accounts, create vast quantities of ammonia gas. It was one of the safest and most confident predictions. But when the James Webb Telescope delivered its verdict, the barcode was clear. There was little to no trace of ammonia. This was a profound and surprising negative result. It was the cosmic equivalent of a dog that did not bark in the night. And in that silence, a beautiful and powerful new hypothesis began to sing. Why would a world that should be full of ammonia have none? The most elegant and compelling explanation is that something is actively removing it from the atmosphere, and the single most effective substance at doing that is liquid water. Ammonia is incredibly soluble in water. It dissolves with remarkable ease. So, if a planet had a thick, hydrogen-rich atmosphere that was sitting directly on top of a vast, deep, liquid water ocean, that ocean would act like a colossal, planetary-scale sponge. It would effectively wash the ammonia out of the sky, sequestering it in the waters below, leaving the atmosphere mysteriously depleted. This single, quiet, negative result, the mystery of the missing ammonia, fits a Hycean interpretation, but is not unique evidence for a globe-spanning ocean of liquid water beneath its hazy hydrogen sky. The barcode of light had not just given us a list of chemicals. It had given us a vision of a new and extraordinary kind of world. The data from the James Webb Space Telescope has given us a series of profound and tantalizing clues. We have found a world with a thick, hydrogen-rich atmosphere. We have found the building blocks of a complex carbon chemistry in the form of methane and carbon dioxide. And most significantly, we have found a deep and mysterious silence where we expected to hear the loud chemical shout of ammonia, a silence that speaks powerfully to the possible presence of a vast and globe-spanning liquid water ocean. These threads of evidence, when woven together, create a breathtaking and beautiful tapestry. They allow us to move, for a moment, from the realm of hard data into the world of informed imagination. They give us permission to dream of a new and extraordinary class of planet, a world that, until now, has existed only in the models of theorists. This is the Hycean world. The name itself is a beautiful and simple portmanteau, a combination of the words hydrogen and ocean. It describes a planet that is defined by these two features: a deep, liquid water ocean that covers its entire surface, all hidden beneath a thick and massive atmosphere dominated by hydrogen. The evidence from K2-18b fits this description so perfectly that it has become the poster child for this new and exciting class of worlds. And so, let us now embark on the next phase of our journey. Let us take the scientific clues as our map and travel in our quiet vessel of the mind to visit this world. Let us descend through its alien sky and gaze upon the shores of its eternal ocean. Our descent begins in the thin, hazy outer layers of K2-18b's atmosphere. The light from the parent star, the dim red dwarf K2-18, is a soft crimson glow. It does not have the harsh, brilliant glare of our own sun. It is a gentler, more ancient light. As we sink deeper, the hydrogen and helium of the upper atmosphere begin to thicken. We pass through high, wispy clouds, perhaps made of frozen methane or other exotic hydrocarbon hazes, which might give the upper atmosphere a soft orange or reddish tint, a vibrant and colorful veil that hides the secrets of the world below. The pressure is building steadily, far more rapidly than it would on Earth. The sky above is no longer the familiar blue we know. The unique physics of how the red light from the star would scatter through a thick hydrogen-methane atmosphere would likely create a sky of a color we have never seen. Perhaps it is a deep, dusky ochre or a soft, moody violet, a permanent twilight color that shifts and deepens as we descend. Lower and lower we go, through dense and turbulent cloud decks. The air outside our imaginary craft is thick, almost soupy, the pressure now dozens or even hundreds of times greater than the sea level pressure on Earth. And then, after a long and gentle descent, we break through the final, lowest layer of cloud. And there, stretched out below us, from one horizon to the other, is a sight that has been the dream of astronomers for centuries: a global ocean. There are no continents. There are no islands. There is only water, an endless, unbroken, and dynamic expanse of liquid, covering the entire world. But this is not the bright, sparkling blue ocean of an earthly postcard. Under the dim, perpetual twilight of the red sun, this ocean would be a dark and moody place. Its surface might appear almost black, perhaps reflecting the deep purples and reds of the sky above. The waves, driven by the winds of the thick atmosphere and pulled by the planet's stronger gravity, would be colossal, slow-moving swells, great mountains of water rising and falling with a patient and powerful rhythm. And what of the water itself? Is it the familiar, life-giving water of our own world, or is it something stranger? It could be a thick, briny, chemical-rich soup filled with the dissolved minerals and organic compounds that rain down from the atmosphere above. And what lies beneath these dark waves? If we were to continue our descent into the depths of this ocean, we might travel down for hundreds or even thousands of miles. The pressure would become so immense, so utterly crushing, that water itself would begin to behave in a way that seems impossible to us. At the very bottom of this colossal ocean, the pressure could be so great that the liquid water would be forced to crystallize, not into the familiar ice we know, but into a strange and exotic form of high-pressure ice, a phase known as Ice 7, which is solid even at incredibly hot temperatures. It is a mind-bending possibility, a warm, liquid ocean whose seabed is made of a floor of solid but hot ice. We have now imagined the stage, a vast and stormy, yet strangely beautiful and potentially habitable world. The clues have led us to this vision of a Hycean planet, and now that we are here, it is time to look for the most tantalizing clue of all. It is time to search for the ghost in the spectrum. We have journeyed to the shore of an impossible sea, guided by the faint and filtered starlight that has traveled for more than a century to reach us. We have conjured a vision of K2-18b as a Hycean world, a planet of eternal global ocean, hidden beneath a sky of hydrogen. The evidence, a quiet story of methane, carbon dioxide, and the mysterious absence of ammonia has painted a breathtaking and self-consistent portrait. But the story does not end here. The James Webb Space Telescope, in its patient and unwavering gaze, was searching for more than just the broad strokes of this alien world. It was listening for a whisper. It was searching for the faintest of all possible signals, for the trace gases that might exist in tiny, almost imperceptible quantities, but which could carry the most profound message of all. And in the complex, data-rich barcode of K2-18b's atmosphere, the telescope detected a ghost. This was not a bold, clear, and unambiguous signal. It was a faint, tentative hint, a subtle dip in the spectrum that was not quite strong enough to be a definitive discovery, but was too significant to be ignored. The chemical fingerprint that the telescope may have found belongs to a molecule with a simple and unassuming name: dimethyl sulfide, DMS. It is not a molecule that inspires the same immediate recognition as water or methane, but for astrobiologists, for the scientists who dedicate their lives to the search for life beyond Earth, the mere mention of this name in the context of a potentially habitable world is enough to cause a surge of profound and quiet excitement. For this simple molecule is the ghost in the machine, the first, faint and tantalizing clue that we might not be looking at a dead world, but a living one. To understand the immense significance of this potential discovery, we must leave the dark, eternal ocean of K2-18b for a moment and return to the bright, familiar oceans of our own home. Here on Earth, dimethyl sulfide is a common and vital part of our planetary ecosystem. It is the molecule that is primarily responsible for that distinct, slightly sulfuric, and strangely beautiful smell of the sea. When you walk along a beach and you smell that fresh, briny ocean air, what you are actually smelling in large part is dimethyl sulfide, and the story of how it gets into our atmosphere is a story of life itself. In the sunlit surface waters of our oceans live vast, microscopic forests of phytoplankton. These tiny, single-celled organisms are the foundation of the entire marine food web, and as a natural part of their life cycle, as they live and die, they release a chemical compound. This compound is then consumed by other microbes, which break it down and release a waste product. That waste product is dimethyl sulfide gas. The gas then bubbles up from the water and into the atmosphere. And here, its role becomes even more crucial. The tiny airborne molecules of DMS act as cloud condensation nuclei. They are the microscopic seeds, the tiny invisible anchors around which water vapor in the atmosphere can gather and condense to form clouds. In a very real and beautiful sense, the breath of the smallest living things in the ocean helps to create the great white clouds that shade our planet and regulate its climate. Here on Earth, there are virtually no known large-scale geological or non-biological processes that can produce significant amounts of dimethyl sulfide. Its presence in our atmosphere is an overwhelmingly biological signature. It is, quite literally, the breath of our ocean. And now, let us return to K2-18b. Let us float again above its dark and endless sea. And let us imagine that the faint, ghostly signal that the James Webb Telescope detected is real. If there is truly dimethyl sulfide in the thick, hydrogen-rich atmosphere of this world, then we are faced with a question of breathtaking importance. Where did it come from? Could there be some strange, unknown, and exotic geological process on a Hycean world that could mimic this signature? Perhaps. But the simplest, most elegant, and most extraordinary explanation is that the process is the same. The whisper that we have heard across 120 light-years of empty space could be the faint, chemical breath of a vast, alien biosphere, the collective exhalation of a trillion microscopic organisms, living and dying in the dark, sunlit waters of a global ocean. This is the very definition of a biosignature. It is not a direct sign of life, not an image of a creature or a coded radio message. It is a subtle, chemical clue that is difficult to explain without the presence of a living system. The potential detection of DMS on a planet that also shows such strong evidence for a liquid water ocean is a 1-2 punch of profound significance. It is, without exaggeration, the single most compelling hint of potential habitability and life that we have ever found on any exoplanet. The signal is still weak. It needs to be confirmed with many more hours of observation. It is a ghost, not yet a body, but its faint, tantalizing whisper has transformed K2-18b from an interesting astronomical object into the primary focus of our great and ancient search. The message in the starlight is no longer just about the chemistry of a distant world. It is now, for the first time, a potential message from the life that might inhabit it. We are left with a vision of breathtaking and profound possibility. The story whispered by the starlight from K2-18b is one of a vast, global ocean, a thick, hydrogen-rich atmosphere, and the faint, ghostly chemical signature of a molecule that on our own world is a product of life. It is a story so beautiful and so hopeful that it is easy to be swept away by it, to declare the great search over, and to welcome our first living, breathing neighbor in the cosmos. But the journey of science is a patient and a careful one. Its heart is not defined by hopeful leaps, but by a quiet and rigorous skepticism. For every beautiful and exciting hypothesis, science must also offer a colder, more mundane, and perhaps more likely alternative. Before we can truly believe the extraordinary story of a living, Hycean world, we must first listen to the quiet voice of doubt, the voice that asks, what if we are wrong? What if the data is leading us not to a brave new world, but to a very old and very common kind of cosmic dead end? This is the voice that proposes the alternative explanation for K2-18b, the great counterargument to the Hycean dream. This is the mini-Neptune hypothesis. This idea suggests that K2-18b is not a scaled-up version of Earth, a rocky world with a vast ocean and a distinct surface. Instead, it proposes that K2-18b is a scaled-down version of a planet like Neptune in our own solar system. In this model, the planet would have a small, solid core of rock and ice, but this core would be surrounded by a massive, incredibly thick and crushing atmosphere composed mostly of hydrogen, helium, and water vapor. Crucially, in this scenario, there is no distinct surface. There is no global ocean of liquid water. Instead, the atmosphere simply gets hotter and denser as you descend, the pressure growing to thousands of times that of Earth's. Eventually, the gases would transition into a strange, soupy, supercritical, fluid state, a realm where the distinction between gas and liquid ceases to exist. This would be a world that is utterly and completely inhospitable to life as we know it. The immense pressures and the searing temperatures deep within this atmosphere, which could reach thousands of degrees, would make the existence of liquid water and the delicate chemistry of life an impossibility. So, how can this profoundly different and deeply sterile model of the planet also explain the data that the James Webb Telescope has sent back to us? The answer is that it can, for the most part, explain the observations quite well. The presence of a hydrogen-rich atmosphere is, of course, the very definition of a mini-Neptune, and the existence of methane and carbon dioxide within that atmosphere is also easily explained by the standard, non-biological chemistry that would occur in such a hot, high-pressure environment. The real challenge for the mini-Neptune model, and the strongest piece of evidence for the Hycean world, is the mystery of the missing ammonia. As we learned, such an atmosphere should be full of it. If there is no liquid ocean to wash it out of the sky, why is it not there? The voice of skepticism has several potential, though not yet proven, answers. Perhaps the ammonia is not truly missing, but is merely hidden from our view. It could be that there are thick, opaque clouds of some other chemical substance that are floating at a high altitude, forming a kind of false ceiling that prevents the James Webb Telescope from seeing the deeper, hotter layers of the atmosphere where the ammonia is abundant. Or it is possible that, at the extreme temperatures and pressures deep inside a mini-Neptune, there are other, unknown chemical reactions that actively destroy ammonia, breaking it down as fast as it is formed. And what of the most exciting clue of all, the faint and ghostly signal of dimethyl sulfide? How could a dead, sterile mini-Neptune produce this potential biosignature? The first and most rigorous skeptical answer is a simple one. Perhaps the signal is not real. The detection is still at the very edge of the telescope's current capabilities, and it has not yet been definitively confirmed. It could be a statistical fluke in the data, a random alignment of noise that happens to look like a real signal. Or it could be a case of mistaken identity, where the spectral fingerprint of another non-biological molecule that we have not yet catalogued happens to overlap with the signature of dimethyl sulfide. But if the signal is real, the challenge for this model becomes immense. Scientists would have to invent an entirely new and unknown abiotic, or non-living, chemical pathway that could produce this specific molecule in a hydrogen-rich atmosphere. As of today, no such pathway is known. And so, we find ourselves at a great and fascinating fork in the road. The very same set of data, the very same barcode of light, can be read in two profoundly different ways. One path leads us to the breathtaking vision of a vast, temperate, and potentially living ocean world. The other path leads us to a much more common, but sterile and uninhabitable gas planet. The voice of skepticism is not a voice of disappointment. It is the voice of scientific integrity. It is the essential force that keeps our hopes and our imaginations anchored to the hard and difficult truth of evidence. The profound mystery of K2-18b is so powerful precisely because both of these possibilities are still on the table. The excitement is not in claiming we have found the answer, but in the patient, ongoing, and deeply human search for it. We have stood at the great fork in the road of our understanding. We have listened with a quiet and necessary respect to the voice of scientific skepticism, the voice that paints a picture of K2-18b as a common, sterile, and lifeless mini-Neptune. This is a possibility we must hold in our minds, a crucial anchor of scientific integrity that prevents our hopes from drifting into the realm of fantasy. But a story with only one path is not a true exploration. And so, now, for the remainder of our journey together, we will choose to walk down the other path. Let us, with a sense of calm and careful wonder, assume that the most extraordinary interpretation of the data is the correct one. Let us build the case, piece by piece, for the breathtaking possibility that K2-18b is not just a habitable world, but a world that is already inhabited. Let us, for a time, believe the whisper. The case for life on K2-18b is not built on a single dramatic piece of evidence, but on a slow, patient, and beautiful accumulation of clues. It is a story of cosmic context, of planetary chemistry, and of a single ghostly molecule. Let us present this case now, as if we were laying out the evidence in a quiet and thoughtful courtroom of the cosmos. Our first piece of evidence is Exhibit A, the location. As we have learned, K2-18b orbits its star squarely within the habitable zone. This is the foundational requirement, the first and most important filter in our search for life. It is the gentle, temperate band of orbits where a planet receives just the right amount of energy from its star for liquid water, the great solvent of life, to potentially exist on its surface. While there are billions of planets in our galaxy, only a small fraction of them reside in this privileged zone. K2-18b is one of these lucky few. It occupies the prime real estate of its own solar system. This is the first crucial piece of the puzzle. Our second piece of evidence is Exhibit B, the presence of a water ocean. This is the clue that elevates K2-18b from a world of mere potential to a world of profound interest. The data from the James Webb Telescope, as we have seen, provides a powerful, albeit indirect, argument for the existence of a globe-spanning ocean of liquid water. The mysterious absence of ammonia in its atmosphere, a molecule that should be abundant, is most elegantly explained by the presence of a vast ocean that has washed it out of the sky. We have not seen this ocean directly, but we have seen its effect on the chemistry of the air above it. So now we have two crucial pieces of evidence lining up. We have a planet at the right temperature for liquid water, and we have strong chemical evidence that this liquid water is actually there, and likely in immense quantities. Our third piece of evidence is Exhibit C, the presence of carbon. The same spectrum of light that hinted at the ocean also gave us a definitive confirmation of a carbon-rich atmosphere, with the clear and unambiguous signatures of both methane and carbon dioxide. Carbon is the backbone of all life as we know it. Its unique ability to form long, complex, and stable chains is what makes the intricate molecules of life, from proteins to DNA, possible. A world with a liquid water ocean and an atmosphere rich in carbon-based molecules has the two most essential and fundamental ingredients for a life-bearing chemistry. We have now found a world with the right location, the right solvent, and the right building blocks. The stage is perfectly set for life to begin. And that brings us to our final and most extraordinary piece of evidence, our star witness, Exhibit D, the ghost in the spectrum, the faint, tentative, but deeply tantalizing signal of dimethyl sulfide, or DMS. As we have learned, on our own planet, this molecule is an almost exclusively biological product, the chemical breath of oceanic plankton. While we must remain open to the possibility of some unknown, exotic, non-living chemistry that could produce this molecule, the simplest and most direct explanation, given the context provided by our other evidence, is biology. When we have found a world that looks like a perfect habitat for life, and on that world, we find a chemical that is almost exclusively made by life, it is a moment for profound and quiet contemplation. Let us now, with this case laid out, allow ourselves to imagine what this life could be like. It would not be a world of complex animals and sprawling forests. The conditions on K2-18b, with its high gravity and its thick, hydrogen-rich atmosphere, would not be conducive to the evolution of large, land-based life. The life we are searching for is almost certainly microbial. But a thriving microbial biosphere is, in its own way, just as miraculous. Imagine the dark, endless ocean of K2-18b. In its sunlit upper layers, under the dim, red glow of its eternal sunset, float vast, unseen forests of alien phytoplankton. But they are not green. Photosynthesis on a world lit by a red star would require pigments that are optimized for absorbing red and infrared light. Perhaps these alien plankton are a deep, shimmering purple, or a profound and efficient black, their entire purpose to soak up every last, precious photon of energy. A great global ocean would be a living, breathing chemical engine, its waters filled with the byproducts of this alien metabolism. The dimethyl sulfide would be just one note in a complex chemical symphony, a conversation of molecules happening on a planetary scale. We are not looking for a single creature. We are looking for the collective breath of an entire living world. And we may have just heard its first, faint whisper. We have just walked down the most hopeful and exciting of all possible paths. We have followed the chain of evidence from a distant, temperate world to a vast and hidden ocean, and finally to the faint, ghostly whisper of a molecule that on our own world is the unmistakable breath of life. We have built the case. We have told the story, and it is a story that is as beautiful and as compelling as any that has ever been told. It is the story that humanity has been dreaming of for millennia, the story of finding life and of finally knowing that we are not alone. And as we rest here in the quiet of this moment, it is a wonderful and deeply moving possibility to hold in our minds. But now we must take another crucial step in our journey, a step that is at the very heart of the scientific process. We must ask the most important and most difficult question of all. Is the story true? And how would we ever know for sure? In the world of science, there is a simple, powerful, and deeply important principle, a phrase most famously articulated by the great astronomer Carl Sagan. It states that extraordinary claims require extraordinary evidence, and there is no claim more extraordinary than the discovery of life on another world. It is a claim that would, in a single moment, reframe our entire understanding of the universe and our place within it. And because the claim is so profound, the burden of proof is immense. The faint, tentative signal of a single molecule, as tantalizing and as hopeful as it may be, is not extraordinary evidence. It is a starting point. It is a clue. It is a single, blurry photograph from a crime scene that demands a deep, patient, and meticulous investigation. The journey from a hint to a proof is a long, slow, and often difficult one. Let us imagine this investigation as it is happening right now in the quiet offices and laboratories of scientists all over the world. The first and most immediate step is confirmation. The initial detection of dimethyl sulfide in the atmosphere of K2-18b was, as we have learned, a tentative one, a ghost in the spectrum at the very edge of the James Webb Telescope's capabilities. The very first task is to dedicate many, many more hours of the telescope's precious time to stare at this world, over many more transits, to see if this faint signal is real. Is it truly there, appearing consistently every time the planet passes in front of its star? Or was it, perhaps, just a momentary fluke in the data, a random alignment of electronic noise that happened to mimic the signature of a real molecule? This process alone could take years of patient observation and analysis. The universe does not give up its deepest secrets easily. If the signal is confirmed, the next, even more difficult step begins: the elimination of all other possibilities. Before scientists can ever claim that they have found a sign of life, they must first exhaust every single conceivable, non-biological explanation for what they are seeing. This is the great work of scientific skepticism. Teams of chemists, geologists, and planetary scientists would begin to create complex computer models of a lifeless K2-18b. They would ask, could some strange and unknown form of high-pressure volcanism on the floor of a global ocean release this gas? Could chemical reactions in the upper atmosphere, powered by the flares from the red dwarf star, create dimethyl sulfide without life? They would have to invent and then test every abiotic pathway, every non-living process, no matter how exotic or unlikely, that could possibly produce this molecule. A biological explanation is only accepted when all other non-biological explanations have been tried and have failed. And even then, the case would not be closed. The third and final step is the search for corroborating evidence. A single biosignature, even a very strong one, is not enough to prove the existence of life. A living biosphere is a complex and messy thing. It does not just produce one strange, out-of-place chemical. It should be a great chemical engine, altering its entire planet's atmosphere in a host of subtle and interconnected ways. So, if there is a vast, planet-spanning ocean filled with phytoplankton producing dimethyl sulfide, what else should we see? Perhaps we should see a slightly higher than expected level of oxygen in the atmosphere. Or perhaps we should see a strange and specific ratio of carbon isotopes in the carbon dioxide, a sign that it is being processed and recycled by living things. The true, extraordinary proof of life will not be a single signal. It will be a whole suite of these interconnected chemical clues, a complex and self-consistent pattern of anomalies that, when taken all together, points to one and only one inescapable conclusion: that the atmosphere is not in chemical equilibrium, because there is a living, breathing biosphere that is actively shaping it. This slow, patient, and deeply skeptical process can feel frustrating. We want the answer, and we want it now. But this process is the very thing that gives science its power. It is a system designed to protect us from our own most cherished biases, from our deep and profound desire to believe the most beautiful and hopeful story. The real message from K218b, for now, is not about the life that may or may not be there. It is a message about the nature of the search itself. It is a lesson in the quiet, humble, and deeply human process of seeking the truth, with patience, with rigor, and with a sense of profound wonder at the mystery itself. We have followed the patient, careful, and deeply skeptical path of the scientific method. We have seen how the faint whisper from K218b must be tested, confirmed, and challenged before it can ever be accepted as a true and definitive message. We have come to appreciate that the journey from a tantalizing hint to an irrefutable proof is a long, slow, and arduous one, a marathon of meticulous observation and analysis that may take years or even decades to complete. And so, we find ourselves in a unique and extraordinary moment in human history. We are living in the great and profound pause between the question and the answer. We are the generation that has heard the whisper, but does not yet know what it truly means. It is a time of suspense, of wonder, and of quiet, global anticipation. And in this great pause, it is worth reflecting on what this moment feels like, and how the mere possibility of this discovery has already begun to change our relationship with the cosmos. For all of human history, our species has labored under a profound and heavy assumption, the assumption of our own cosmic loneliness. Though we have dreamed of other worlds and other lives, our lived reality, the one confirmed by all our science, has been that we are a singular and unique phenomenon. We are the sole bearers of consciousness, the only storytellers, in a universe that is vast, beautiful, but ultimately silent and empty. This sense of cosmic solitude is woven deeply into our philosophies, our religions, and our art. It has given us a sense of immense importance, but also a sense of immense isolation. We have always believed, completely and utterly alone. The whisper from K218b, that faint, ghostly fingerprint of dimethyl sulfide in a distant sky, has, for the first time, introduced a tiny, beautiful crack in that great and ancient wall of loneliness. Even as an unproven and tentative clue, it has fundamentally shifted our perspective. The night sky itself feels different now. The countless, distant points of light are no longer just symbols of our isolation, reminders of the vast, empty distances that separate us from everything else. They are now imbued with a new and vibrant sense of potential. Each star is no longer just a distant, fiery furnace. It is a potential sun, the center of a potential family of worlds. And any one of those worlds, we now know, might be like K218b, a place of water, of chemistry, and perhaps of life. The universe, which may have felt cold, sterile, and indifferent, now feels pregnant with a thrilling and beautiful possibility. The great silence has not been broken, but for the first time, we have the distinct and wonderful feeling that somebody, somewhere, may be about to speak. In a sense, this moment marks the beginning of the end of a certain kind of human innocence. Our history has been a story of a slow and often painful realization that we are not as special as we once believed. This is a process that has been called the Great Demotion. First, the Copernican revolution taught us that our Earth was not the center of the universe, but just one of several planets orbiting a rather ordinary star. Then, in the early 20th century, the discoveries of Edwin Hubble taught us that our Milky Way galaxy was not the entire universe, but just one of billions upon billions of other galaxies, a single grain of sand on an infinite cosmic beach. Each of these discoveries was a profound humbling, a step away from our self-appointed pedestal at the center of all things. The confirmation of life on another world, even microbial life, would be the next and perhaps the final and most profound step in this great demotion. It would prove that the one thing we still held as uniquely and miraculously our own, the phenomenon of life itself, is not a singular, divine miracle, but perhaps a common and natural outcome of the laws of chemistry and physics. This would be the ultimate act of cosmic humbling, and yet it would also be a profoundly unifying and uplifting realization. To know that we are not a lonely accident, but part of a great, living cosmic family would be the most powerful antidote imaginable to our terrestrial conflicts and our petty tribal divisions. To know that the universe is alive would connect us not just to each other, but to the cosmos itself in the most intimate and meaningful way possible. And so we are left to live, for now, in the beautiful and suspenseful space between the old story of our loneliness and the potential new story of our connection. The whisper from K218b has already changed us, regardless of the final answer. It has given us a new and more hopeful story to tell ourselves about the universe. We are no longer the species that can only ask, "Are we alone?" We are now the species that has finally built the tools to listen for an answer. We have built an eye so powerful that it can detect the faint chemical breath of a world that is orbiting a star 120 light-years away. And in that achievement, in that quiet and patient act of listening, we have already found a new and more mature place in the cosmos. We are the detectives in the greatest mystery of all time, and the investigation has just, in our own lifetimes, truly begun. We have been resting, together, in the profound and suspenseful pause between a great cosmic question and its potential answer. We have felt the weight and the wonder of this moment, the feeling of a species standing on the very precipice of the most important discovery in its history. But now, for the next step of our journey, let us take a gentle leap of imagination. Let us travel forward in time, to a day in the not-too-distant future. A day when the long, patient, and skeptical work of science is finally complete. A day when the signal from K218b has been confirmed, when all other possibilities have been exhausted, and when a quiet, sober, and global consensus has been reached. Let us imagine the world on the morning after we learn, with scientific certainty, that the whisper from that distant world is indeed the chemical breath of life. What would change? How would this single beautiful fact, the knowledge that we are not alone, ripple outwards to transform our world and ourselves? The first and most profound change would be a quiet and permanent shift in our collective worldview. The knowledge that life exists beyond Earth would cease to be a matter of speculation and would become a fundamental fact of our existence. It would be a truth taught to school children with the same certainty as the fact that the Earth is round and that it orbits the Sun. This would not be a loud or a violent revolution, but a deep, slow, and irreversible change in the very foundation of human thought. The age-old story of our loneliness would be over, replaced by a new and much grander story of our connection to a living cosmos. This discovery would launch a golden age of a brand new science, comparative astrobiology. For the first time, we would have a second data point in our study of life. We would no longer be limited to studying the one single example of life that arose on our own planet. Scientists would work for centuries to decipher the secrets of the life on K2-18b, from its faint atmospheric signals. Is its chemistry also based on carbon? Does it use DNA to store its genetic information? Or has life on another world found an entirely different way to be? These questions, which have been the subject of pure fantasy for so long, would become the central driving questions of a new and vibrant field of scientific inquiry. This new science would help us to understand what is truly universal about life and what is merely a local terrestrial quirk. It would be the beginning of our search for a universal biology. This new understanding would, in turn, trigger a deep and necessary evolution in our philosophies and our spiritual traditions. The confirmation of a second genesis of life would be the final and most powerful step in humanity's great demotion. It would be the definitive end of the idea that humankind is the pinnacle, or the central purpose, of creation. To know that life is not a singular miracle, but a common cosmic process, would instill in us a new and profound sense of humility. It would gently ask our great religions and spiritual traditions to expand their perspective, to find a place in their cosmologies for a universe that is not human-centric, but life-centric. For many, this would not be a crisis of faith, but a beautiful and profound confirmation of a creative, generous, and life-giving universe, a divinity that expresses itself not just on one world, but potentially on billions. And with this new perspective would come a new sense of purpose for our future. The search for life in the universe would transform from a fringe, speculative science into the central, unifying quest of 21st century astronomy. We would build new and even more powerful telescopes, great golden eyes designed not just to find planets, but to patiently stare at them for years, reading the faint, chemical stories written in their skies. We would create a great library of potentially living worlds, each one a new and fascinating chapter in the cosmic story of life. The search for extraterrestrial intelligence, or SETI, would be re-energized with a new and powerful logic. If simple microbial life is common, then perhaps, given enough time on the trillions of planets around the trillions of long-lived red dwarf stars, complex and even intelligent life might also be out there, waiting to be found. The discovery would also force us to mature as a species. We would be forced to have a deep and serious global conversation about what has been called the Prime Directive. If we have found a world that is teeming with its own unique life, what are our responsibilities? Do we have the right to interact with it? To potentially contaminate it with our own biology? Or must we become its silent, humble, and respectful guardians? The confirmation of life on K2-18b would act as a great, clarifying mirror. It would reflect back upon us our own terrestrial divisions, our own tribal conflicts, and show them for what they are: the petty squabbles of a young and isolated species. The knowledge that we are part of a larger, living family, would, one hopes, and unifying force, the catalyst for a new and more peaceful chapter in our own human story. We have imagined the great, sweeping changes that the confirmation of life on K2-18b would bring to our world. We have seen how it would transform our science, reshape our philosophies, and provide a new, unifying story for the future of our species. These are the grand societal shifts, the headlines and the history books of a new human era. But now, as we drift closer to the quiet harbor of sleep, let us explore the most intimate and perhaps most meaningful change of all. Let us consider how this profound new knowledge would transform the personal, quiet, and solitary experience of being a single human being, standing alone in the darkness, looking up at the night sky. For all of our lives, the night sky has been a place of a specific kind of beauty. It has been a beautiful but largely lonely landscape. We have looked up and seen the history of our own ideas reflected in the constellations, the mythological figures of our ancient past. We have seen the planets of our own solar system, familiar neighbors that we know to be magnificent, but sterile, worlds of rock and gas. And we have seen the countless distant stars, knowing them to be other suns, but seeing them as symbols of the immense empty distances that separated us from everything else. The sky has been a museum of our past and a mirror of our solitude. But on the day after the great discovery, the sky itself would be transformed. The night would cease to be a museum and would become a living garden. Every single point of light would be imbued with a new and vibrant potential. We would look up at the constellation Leo, and we would no longer see just the outline of a mythical lion. We would see a landmark. We would see the home of our first known living neighbors. We would be able to point to that specific fate star and say, with a quiet and profound certainty, there, the life is there. That knowledge would change the very texture of the darkness. The stars would no longer be cold and distant points of light. They would be other suns, other campfires, each one potentially warming its own family of worlds, each one a potential home for its own unique expression of life's tenacious and creative spirit. The sky would be filled not with emptiness, but with neighbors we have not yet met. This new perspective would also change our relationship with our own world. The word Earth for our entire history has been synonymous with the word life. But in this new reality, that is no longer true. Our beautiful blue and white world is no longer the universe's solitary miracle, but our own unique and precious version of a cosmic phenomenon. This does not diminish the Earth. It makes it even more precious. It would allow us to feel a new and deeper sense of kinship with the life of our own planet. We might look at the microscopic plankton in our own oceans with a new sense of reverence, seeing them as our terrestrial cousins to the great alien biosphere of K2-18b. The pale blue dot, that famous, humbling image of our world from a great distance, would no longer be a portrait of our loneliness, but a portrait of our place in a great cosmic archipelago of living islands. And the great silence, the profound and enduring quiet of the cosmos that we have so often found unsettling, would be reinterpreted. It would no longer be the silence of an empty and desolate room. It would become the silence of a deep and ancient forest at midnight. We may not be able to see or hear the countless forms of quiet, hidden life that are teeming all around us, but for the first time, we would know with certainty that they are there. This transforms the silence from a source of existential dread into a source of deep and peaceful patience. It is a silence that is filled not with absence, but with a living, breathing potential. It invites us not to shout into the darkness, but to listen more closely, more carefully, and more humbly. This is the quiet revolution that the discovery would bring to each of us. It would not change the practical details of our daily lives. We would still have our joys, our struggles, our responsibilities. But it would change the fundamental context in which we live those lives. It would provide a new and constant background hum of wonder, a secret and profound knowledge that could be a source of immense comfort. To know, in a moment of personal sadness, that you are part of a living universe. To know, in a moment of great division, that all of humanity shares this one tiny living island. This knowledge would be a quiet internal anchor, a permanent shift in perspective that would allow us to hold our own human dramas with a little more grace, a little more humility, and a little more peace. The universe would no longer feel like a cold and mechanical place. It would feel, for the first time, like a great, living, and breathing organism. And our relationship with it would change from that of a lonely observer to that of a true and humble participant in its grand and unfolding story of life. We have explored the quiet internal revolution that the discovery of life on K2-18b would ignite within each of us. We have felt how it would transform our personal relationship with the night sky, and how it would imbue the great cosmic silence with a new and beautiful sense of living potential. It would be a new foundation for our worldview, a new context for our human lives. But science and the human spirit of exploration does not rest on a single discovery, no matter how profound. A single answered question is never an end. It is always the beginning of 1,000 new and even more exciting questions. And so, in this part of our journey, let us look to the future once more. Let us imagine the path forward. In a world that now knows it is not alone, what would be the next steps in our great cosmic journey? What would humanity do next? The first and most immediate consequence would be a laser-like focus on the source of this profound revelation, K2-18b itself. The planet would be transformed from a faint, distant object of curiosity into the most important scientific subject in human history. The James Webb Space Telescope and its successors would dedicate a vast and unprecedented amount of their precious observational time to this one single world. The initial tentative detection of dimethyl sulfide would be just the first word in a long and patient conversation. Scientists would begin a multi-year and likely multi-decade campaign to build a complete and detailed portrait of this living world. They would observe hundreds of transits, patiently gathering photons of light one by one to build up the faint signal from the atmosphere with unshakable certainty. They would confirm the presence of dimethyl sulfide beyond any shadow of a doubt. And then the search would broaden. They would hunt for a whole ecosystem of other chemical clues. Using the same delicate art of transmission spectroscopy, they would search for the faint, telltale signatures of other gases that could point to a thriving biosphere. Is there a small but persistent amount of oxygen or ozone in the atmosphere, a potential byproduct of alien photosynthesis? Are the ratios of the different isotopes of carbon in the carbon dioxide askew? In the same way that life on Earth preferentially uses the lighter isotopes of carbon, leaving a distinct biological fingerprint. This would be the slow, meticulous, and deeply rewarding work of a generation of scientists, to move beyond the single clue and to paint a rich, detailed, and undeniable chemical picture of an alien biosphere at work. With enough data, they might even be able to create a crude, global map of the planet's atmosphere, detecting how the chemistry changes between the perpetually sunlit day side, the frozen night side, and the temperate, life-bearing twilight of the terminator zone. We would be creating the very first weather report for another living world. But the discovery would ignite more than just a focus on a single planet. It would trigger a revolution in the entire field of exoplanet science. The confirmation that a Hycean world could indeed harbor life would be a monumental discovery. These worlds, the sub-Neptunes, are the most common type of planet in our galaxy, and we would now know that many of them could be potential cradles for life. This knowledge would trigger a great new survey. Astronomers would compile a new and urgent target list, a catalog of all the known sub-Neptune planets that orbit within the habitable zones of their parent stars. Each one of these worlds would become a new and exciting candidate, a new door to knock on in our search for our cosmic neighbors. To study these worlds, we would build new and even more powerful tools. A new generation of great space telescopes would be designed and funded, telescopes even larger and more sensitive than the James Webb. Their primary mission being not just to find planets, but to patiently and systematically analyze their atmospheres for the chemical whispers of life. The great search would accelerate, moving from the discovery of a single, living world to the profound and statistical question of just how common life is in our galaxy. Are we living in a cosmic desert with only a few rare oases of life separated by vast, sterile voids? Or are we living in a lush, cosmic jungle, a galaxy that is teeming with life in a billion different and beautiful forms? And finally, the confirmation of even simple microbial life would breathe new and powerful life into the oldest and most hopeful of all our searches, the search for extraterrestrial intelligence, or SETI. If the universe has proven that it is capable of creating life, then it dramatically increases the odds that somewhere on some ancient world that has had billions of years of peaceful evolution, some of that life may have evolved into a complex, intelligent, and even technological form. The great silence of the cosmos would seem less like a definitive answer of our loneliness, and more like a challenge we have not yet overcome. We would build vast new radio telescope arrays, perhaps on the silent, radio-quiet far side of our own moon, to listen with a new and more profound sense of purpose. We would be a species that is not just looking, but is now actively and patiently listening for the first, faint, and transformative signal from another thinking mind. The future of a humanity that knows it is not alone would be a future defined by a new, outward-looking sense of purpose, a quiet and deeply hopeful journey of cosmic listening. Our journey together is now turning towards its quiet and peaceful conclusion. We have traveled across an almost unimaginable gulf of space to visit a distant twilight world. We have learned the beautiful and delicate art of reading the secrets of its atmosphere in a single, faint beam of starlight. We have imagined it as a great and majestic Hycean world, a planet of eternal ocean and endless sky. We have listened for the faint, ghostly whisper of a molecule that could be the very breath of an alien biosphere. And we have, with a quiet and necessary humility, also considered the colder, more skeptical possibility that we may be mistaken. We have contemplated the profound and permanent ways in which the confirmation of life would transform our science, our philosophies, and our own personal sense of place in the cosmos. The great cosmic part of our story is now complete, and so it is time to bring our awareness back from the distant shores of K2-18b and into the quiet, familiar, and peaceful landscape of our own being, as we prepare for the gentle and healing journey into sleep. The story of K2-18b, with its two branching paths of possibility, is a perfect mirror for the nature of our own minds. Our minds, in their constant and restless quest for certainty, are always trying to choose one story. We want to know definitively if the hopeful story is the true one, or if the skeptical story is the right one. We crave the final answer. We want to know how the story ends. But tonight, our journey has taught us a different and perhaps more peaceful kind of wisdom. The true peace is not found in choosing one path, but in learning to rest with a quiet and gentle awareness in the beautiful and open space of the mystery itself. Let us imagine that the two possibilities for K218b, the living ocean world, and the sterile mini-Neptune are two distant shores. Between these two shores lies a great, calm, and quiet ocean of the unknown. And your awareness is a small, solitary boat, resting peacefully on the surface of this water. You do not need to row frantically towards the shore of hope. And you do not need to anchor yourself to the shore of doubt. For tonight, your only task is to rest in the gentle rocking stillness of the water itself. It is to find your comfort not in the destination, but in the quiet, patient, and wondrous nature of the journey. This is the art of holding a great question, not as a problem to be solved, but as a sacred space in which to rest your mind. And so, as you lie here now, in the stillness of your own room, let us begin the simple and gentle process of finding this quiet harbor within yourself. Bring your awareness to your body. Feel the gentle, solid, and reassuring contact of the bed beneath you, holding you, supporting you completely. You do not need to hold yourself up anymore. You can let go. Feel the gentle touch of the air on your skin and the soft, comforting weight of the blankets. This is your safe harbor. This is your quiet corner of the cosmos. Now, bring your awareness to your breath. There is no need to change it or to control it in any way. Simply notice it. Feel the gentle, natural, and easy rise on the inhale, and the long, slow, and complete release on the exhale. Your breath is the gentle tide of your own personal ocean. It is the most ancient and reliable rhythm you will ever know. It is your anchor in the calm and peaceful waters of the present moment. If any thoughts should arise, as they naturally will, see them for what they are. They are like the faint, ghostly signals from a distant star, whispers from the past, or projections into the future. You do not need to analyze them. You do not need to follow them. You can simply acknowledge their presence, and then, with a gentle and loving kindness, guide your awareness back to the simple, physical sensation of your breathing. The rise and the fall, the inhale and the exhale. This is your practice, and with every breath, feel yourself sinking just a little bit deeper into a state of quiet and profound rest. The great cosmic mystery of K218b will be there for you to contemplate tomorrow. But for tonight, the only mystery you need to rest in is the simple, beautiful, and peaceful mystery of your own being, here and now. You have arrived now at a place of deep and profound stillness. The great cosmic journey is complete. The questions have been asked, the mysteries have been contemplated, and the mind has been expanded by the immense and beautiful possibilities of the universe. Now, all that is left is the quiet. All that is left is the peace. Your body is heavy and relaxed. Your mind is calm and open. And you are now standing on the shore of the last and most welcoming of all destinations. The great, silent, and healing ocean of deep sleep. There is no effort needed to begin this final journey. There is no destination to strive for. There is only the simple, gentle, and natural act of allowing. It is time to let the current carry you home. Let us use the vision of K218b, our distant ocean world, as our final guide. Imagine that you are standing on the shore of its eternal, twilight sea. The dim red sun hangs forever on the horizon, casting a soft crimson glow upon the slow, majestic waves. The air is still and calm. The great dark ocean before you is not a place of turbulence or of fear. It is an ocean of profound and absolute peace, an ocean of pure, restorative potential. It is the great, subconscious sea of your own being, and you have arrived here at the end of a long journey, ready to rest. Feel the gentle, rhythmic pulse of the waves, a slow and steady rise and fall, a sound that is perfectly in sync with the quiet and easy rhythm of your own breathing. With your next gentle exhale, imagine yourself taking a single, easy step forward, leaving the shore of the waking world behind you, and allowing the calm, warm, and comforting water to embrace you. Feel all the weight, all the tension, all the worries of the day simply dissolving away, washed clean by this gentle cosmic tide. You are not falling. You are not struggling. You are floating. You are held. You are supported. You are completely and utterly safe. And now you can feel a gentle, imperceptible current beginning to pull you away from the shore, out into the deep, quiet, and peaceful heart of the water. This current is the natural pull of sleep itself. You do not need to resist it. You do not need to help it. You simply need to allow it to carry you. With every breath, you feel yourself drifting a little farther, a little deeper, into this state of perfect tranquility. The dim, red light of the star on the horizon becomes softer, more distant. The cares and the thoughts of your waking life are now on a shore that is fading from view. You are a silent traveler, floating weightlessly and peacefully in a great, dark, and comfortable sea. There is no destination, only the gentle and pleasant sensation of drifting. There is no time here, only the steady, quiet rhythm of your own breath, the rise and the fall, the inhale and the exhale. Feel your awareness itself beginning to soften and dissolve, like a single drop of rain merging with the vast and endless ocean. The boundary between you and the deep, restorative peace is fading away. You are letting go now, drifting, floating, sinking gently into a place of profound comfort and safety, a place of deep and dreamless and healing rest. Sleep is here now, a gentle presence, a welcome friend, ready to take you into its quiet embrace. You can surrender to it now. Let go of this last, final thread of wakefulness and allow yourself to drift away completely. There is nothing left to do. There is nothing left to hear. There is only this deep and profound and comfortable peace. Rest now. Just rest. The journey continues, always calmly, always at the pace of the universe.